Shall we get started again? So, okay, so before lunch, we looked at some cases of logical circuits. So specifically those ones that satisfy decomposability, determinism, and then we saw a few different ways we could maybe take another probabilistic model and then compile them to do inference on using the circuits, right? So so I also want to talk a bit more about other kinds of logical circuits that have stronger properties that will later let us actually compute harder queries, like the ones that were teased earlier, including actually talking about probabilities of logical events and so on. So some examples, starting from BDDs, binary decision diagrams. Then if we say in that BDD, for any path, you can only have a variable occurring once, kind of read once. Branching program like circuits would be FBDDs. If you enforce a kind of ordering of variables, a total order on all of the paths, we have OBDDs used for a lot in like verification and so on. And then kind of a generalized version, we have also some tangential decision diagrams, which I'll get to the properties about it in a bit. This is just to kind of show you that often we use this kind of decision DAG representation for BDDs, right? Like each of these being a decision node, saying, if X is true, you go this way. If X is false, you follow this dotted line. You can kind of do a simple translation into the sort of circuit language that we've seen so far using AND and OR gates, and these are equivalent. So you can kind of think of also BDDs as kind of circuits with different properties, which I'll talk about. So for SDDs, we're going to enforce essentially a stronger kind of decomposability and also a stronger notion of determinism. Right? So, so this is actually an example of an SDD. So we have this property called structured decomposability, basically meaning that how the circuit partitions the variables at every OR gate is dictated by this binary tree called V tree. Right? So it's just a binary tree with variables associated with the leaves, and this is telling us how to decompose variables at every AND node. For instance, all of these AND nodes at the very top corresponds to this root of the V tree, so that you can see on the left side, you have variables L and K. On the right side, you have variables P and A, and that is true for all these AND nodes. And then this, of course, happens for every AND gate. So now the one below here is decomposing the variables into L on one side, K on the other side, corresponding to this internal V tree node. And then I mentioned we will also have a stronger notion of determinism. So sometimes called partition or strong determinism, basically says that, so it is, we want every OR gate to be deterministic, not just deterministic, but also deterministic specifically on the left child of this sort of decision node. Right? When you have a pair of OR and AND gates, you want it to be deterministic specifically on these left child. So this, this implies determinism, but not every deterministic circuit is going to be strong deterministic. Makes sense?
What do you mean deterministic on the left side?
So basically, essentially, if you look at these three edges or these three inputs, you want at most one of these to be true for any any joint assignment. Instead of just the inputs to the OR gate, when you have decision nodes, you actually want specifically the left child of the decision node to be deterministic. So for instance, we could have determinism where for an input, let's say this one evaluated true. Like let's say this is red, this is blue. Right? In that case, this top node will still be deterministic, right? But then that would violate strong determinism.
I don't know if people are familiar with FBDDs. So, okay, let me backtrack one more. You think about that determinism. The problem is checking determinism is actually hard. You need to check that two formulas are mutually exclusive, and this is probably co-NP complete. Not probably, certainly co-NP complete. Yeah, so correct me if I'm wrong. Okay, so we cannot check determinism easily. There is a trivial way to enforce determinism. This is what FBDDs are doing. Namely, for each OR node, there is a single variable for which the left child is conjoined with a negation. The right child is conjoined with a variable itself. So these two children can never be true at the same time because this variable controls determinism. SDDs relaxes a little bit. Instead of controlling over a single variable, you can control over multiple expressions, which are the left child of that end node. I think that is a progression that I have in mind to understand SDDs. Yeah, sorry.
Yeah, no, that's a great explanation. So basically, like we have here decision nodes deciding based on a single variable, right? So instead of a single variable, you could imagine deciding based on some logical formula.
So, is this for efficient model checking that if the left node is false, then you do not have to check the right node? For seeing application?
So one definitely you can do logic. I don't think it's necessary. It's not necessary.
What is this? What are SDDs giving that is not given by the previous compilation?
Oh, okay, yeah. So I'll actually touch on some query classes, especially if we have a lot of examples when you go through like probabilistic inference. So in the beginning, the queries you mentioned include like marginal map, which is kind of doing map over a marginal distribution, and some other like information theory queries which will actually use this property.
Okay, so when you say the idea is that the left children are mutually exclusive, but if they can be arbitrary formula, is it easier to check that they are mutually exclusive? Because when it's a single literal, of course, it's clear that it's mutually exclusive.
You could have the right children being always empty, and then you would be back to the previous situation. So,
well, it's I think checking determinism to begin with is hard.
Okay, but
so, yeah.
Also in the case of SDDs, it's
also hard. So you it's something you could kind of enforce more as a syntactic and like structural property as you're compiling, for example.
Okay.
Yeah, I think it can be done efficiently because you can just go join these things in polynomial time and check it, and they're canonical, so you can check if their conjunction is equivalent to a false SCD, and then you know. So I think you can still check efficiently.
I feel
if you have an SDD only, right?
Not for general.
Right, but if in general you're given an arbitrary circuit, you're trying to check strong determinism, then at least as hard as just checking determinism.
Are they structured, the SDDs? Sorry.
the end gate is structured.
The end gates have to be structured.
Yeah.
Okay, so then you can conjoin. Thanks.
Okay, and then by connecting SDDs to what was mentioned earlier on OBDDs, basically, we can think. I think this already came up slightly. So you can think of SDDs as a generalization of OBDDs, or OBDDs being a subset of SDDs. Basically, that so these two are equivalent circuit. Don't worry about this circles and boxes here. Basically, the circles mean OR gates. The boxes mean take product of or take conjunction of these two. Right? So this is equivalent to this OBDD, and in particular, any SDD that has, or any OBDD, you can think of as SDD having this kind of linear, or right linear to be precise, V tree, where you are always branching on one variable on the left side. Okay, so where can we actually use this, right? So I think this question came up a couple times. So one example that was teased earlier is actually computing the probability of some logical events. For example, this one where you have where you're asking, okay, what's the probability of probably that there will be traffic jam on my route to campus? The route given as some kind of disjunction over there being some traffic jam in all the streets that's in your route. Okay, so this is kind of a simple example of a logical formula, but you could imagine asking this kind of question of, given some more complicated kind of logical formula, what is the probability that will be satisfied? And another example we saw was I think he was talking about the gelato and trying to do like controlled language generation, where you're given some like logical constraints that you want to satisfy in your in the generated language. So that is also kind of computing this probability of well, technically it's computing the probability of that formula being satisfied, and also actually sampling from that distribution. Okay, so how do we actually do this? Now this is kind of our first example query where we're going to have two circuits involved. So what we do is for instance, in this example, when you want to calculate the probability of some logical event, we're going to compile that logical formula into a logical circuit. And if this probability distribution is also given as a circuit, we can actually compute this query tractably, of course, given some structural properties. Right? Also, this is kind of the first example where your query size is not trivial. To define your query, we're using a logical formula or a logical circuit. So now trackability means that you want to compute queries in polynomial time in both the size of not just your probabilistic circuit, but also your logical circuit defining your query. Right? Okay. And so the properties that we need in this case is going to be first smoothness, and this stronger notion of decomposability I mentioned, structure decomposability. And then also on the logical circuit, we want determinism to be satisfied as well. And particularly, not only we want both the probabilistic and logical circuits to be structure decomposable, we actually want them to be structure decomposable with respect to the same V tree, meaning you have two circuits that will decompose variables in exactly the same way. Okay, so how does the inference actually work? So similar idea, like we go from we start at the root of the circuit and see how we can break the query down to queries on the inputs, or like input gates or subcircuits, starting from the root all the way to the leaf node. Okay, so let's start at the very top. We have so basically we want to compute this probability. Oh yeah, here we go. The probability of a logical formula given by the circuit. So we're looking at these two nodes here. Okay? So we're looking at the pair of nodes here, and we know that this is smooth, and the logical OR gate is smooth and also deterministic. So what that means is the actual formula we want to compute is going to look like this. So the probability decomposes into sum of probabilities given by the child nodes, right? Highlighted in blue here. And then this logical formula is just a disjunction of the formulas given by the child. Now, because this is deterministic, what we can say is the probability of this disjunction is just sum of their probabilities, right? Some of the probability of the small child logical functions. Make sense? Okay. So what we've done here is taken this query at the top and turned it into another weighted sum of queries, looking at every pair of probabilistic circuit child node and the logical circuit child node. Okay, so now we've pushed it down one layer. So what happens at product and AND gates? So here we said that they are both structured decomposable with respect to the same V tree, meaning they both they both break down into product or conjunction of two functions, each depending on the same variable. So the left one depends on the same variable as the left child of the logical circuit, and then the right child of the probabilistic circuit depend on the same variables as the right child of the logical circuit. Basically, this probability of a formula just decomposes into taking the product of the probability of each pair of nodes, the left children and then the right children. So all we do is just keep doing this, from the root all the way down to the leaves. Where at the leaf, the assumption is that you can, for instance, just compute the probability of a single literal very easily. Combining these together, again, the dynamic programming algorithm is basically roughly at each layer, because this is structured decomposable. You can think of every layer of the circuit being associated with kind of a layer of the V tree. So at every layer, we look at all pairs of probabilistic circuit node and the logical circuit node, compute the probability of the logical event. So compute this PR query, and then combine them using the formula that I just showed you in the last couple of slides. So again, this gives us this single feed-forward evaluation that lets us compute a probability of a logical event. Okay. So in addition to the PR query that I just talked about, so there are some more examples of queries that you can compute if you have structured decomposability, and most of this also strong determinism. So for instance, if you have an SDD or probabilistic version of SDD and you had the right V tree, you'd be able to compute marginal map. We just went over this probability of logical event, and also some information theoretic queries, which I'll also talk a little more about later, and some operations as well, right? So so far we've been talking about answering queries computing probabilities on circuits. What you can also do is combine two circuits. For instance, in the logic domain, this is very natural to do, trying to like conjoin or disjoin circuits. You could do something similar with probabilistic circuit, trying to like multiply distributions and different operators, which I'll also talk about some of those operators later on. But they also kind of require that you have this structure decomposable property, right? So with this additional properties, there's a lot more query you can answer tractably. So that's why, depending on what kind of reasoning queries you would care about at the end, that would dictate your compilation language. And when you're compiling your probabilistic model or some CNF formula, you would decide what properties you want to enforce based on what you want to do with the compiled circuit at the end, right? That was kind of the earlier session before lunch, and this one is combining how probabilistic circuits are related to logical circuits, and how we can compile these circuits to do inference. So next, I want to talk about how the properties that give you this trackability actually affect your circuit size, right? Because of course, trackability is of course defined with respect to the size of the circuit, right? We're saying, okay, you're going to be linear time or polynomial time in the size of your circuit. If your circuit size blows up, that trackability isn't really meaningful. Okay? So we want to study how different properties affect the size of your circuit. In this part, of course, there's a lot of literature in studying relative expressive efficiency or succinctness of different circuit families. I'll kind of give a few pointers and highlight some results, but I won't go over the details too much. But I like to kind of give you pointers for you to go and see if you're interested, and also give some examples of like open problems there. Okay, so let me let's first formally define what I mean by succinctness. So we say a family of circuits, M1 is at least as succinct as another family, M2. If you can take any circuit in the second family, turn it into a circuit in the first one without changing what function it represents, and in polynomial size. Right? And here I kind of vaguely said function. This definition applies to logical circuits, probabilistic circuits, and other semi-rings as well. Basically, if it's logical circuit, we're talking about Boolean functions. If it's probabilistic circuit, we're talking about the likelihood function. Okay?
Sorry, I'm confused here by the direction. So M1, you want to write M1 is less than M2. So does it mean my interpretation would be that every circuit in M1 can be simulated by 1 and M2?
No, so if you think about, let's see, so if we say M1 is just the family of all circuits, right, with no properties, with no constraints, then okay, that's clearly at least as succinct as any other subfamilies, right?
I see. Okay.
And in that case, we can say any, for example, decomposable circuit is a circuit. So this direction is always satisfied.
It's the opposite direction of how you would normally write a reduction.
Yeah. So,
yes,
by analogy with the computational model of circuits, shouldn't there be also some conditions here about related to that? Because I am concerned about, for example, the the subtleties that occur there when you have uniform families of circuits or non-uniform families of circuits. This is not, I understand when you look at this definition, you're thinking how to apply it to BDDs and OBDDs and so on. But if you want a general definition for this, there is no computational aspect related to it as far as you know.
Can you clarify what you mean by like uniform
I
and
mean,
non-uniform?
Do you compute M1 from M2? I think that's what
for example, for succinctness, but more generally, yeah.
This is not about computing, it's just about the existence, right?
Yeah, and we'll really characterize these families of circuits based on the structure properties and not so much about, for example, like the parameters and like arbitrary kinds of like delineations you can make in the circuit families. Also, when I say family of circuits, I'm mainly talking about circuits that satisfy properties X, Y, and Z. And also I'll later talk a little more about, is that the right characterization?
And the size of the circuit is the number of nodes. So every node has binary inputs. That's correct. The size of the circuit.
Every
Number of edges.
You allow unbounded fan out or fan in, so number of edges.
yeah. Okay. Is this slide okay now? Okay. Oh, and just again, mention this, but yeah. So this is how we would write that M1 is at least as succinct as M2, and of course, if we want to write strictly more succinct, then the one direction is true, but not the other. Right. So this is kind of the succinctness map from Nadarish and Pierre Marquis' knowledge compilation map that's characterizing sort of relative succinctness between these families of circuits. For example, NNF is all NNF circuits, and this is saying it's strictly more succinct than a DNNF, which is a decomposable NNF, so on, right? And here we get this strict succinctness ordering from these circuit families that we've seen. So decomposable NNF to deterministic and decomposable NNF, and then to FBDD, OBDD. I won't go over like all pairs here, but just to kind of like give an example of one of these strict separation. So if you're looking at, so this is saying taking a decomposable circuit and then trying to make it deterministic is hard. So sort of conditional hardness is sort of easy to show. You can take, for instance, any query that you can compute with deterministic and decomposable circuit, but not with a decomposable circuit. One example could be like trying to do counting in DNF, which is going to be a DNNF, right? Because it's because it's decomposable, you can say it's decomposable, but then counting in DNNF is actually sharply hard, meaning you can't really you can't make it deterministic in polynomial time unless the polynomial hierarchy collapses.
Well, I bet you that to get this kind of result, you would need a more refined definition of more succinct, that would have some computational aspects. I mean, for upper bounds, sure, but for this kind of reductions.
There are like Karp-Lipton theorems that say like MT is in equality, like non-uniform, then polynomial hierarchy collapses. So it's probably uses something like this. Yeah, there are connections like that from non-uniform to uniform.
Sorry.
And then we also kind of slightly more recently, we also have an example actually showing that this separation can be proven without this condition. So there's actually an exponential lower bound or exponential separation between BDNF and GNF. I don't really understand the details of the proof, so I'll just kind of mention that how this exponential separation was shown is actually excluding a connection between circuit sizes and multiple partition communication complexity. And I believe Stefan Mengel, who's a co-author on this paper, I think he'll be here at some point. So if you're interested.
Do you happen to know the Sauerhof function? Do you know what it is? Just if you know it.
Yeah, I'm not really familiar with the intuition of the function.
Okay.
Yeah, I just know that it's something that's relevant in communication complexity, and it kind of basically some result about the sort of Sauerhof function and the hardness of the communication protocol sort of implies this exponential lower bound. All right. So one more example of sort of succinctness result between two families of circuits. So earlier I said that we saw that OBDs are actually kind of subclass of SDDs, right? Basically, every OBDD you can think of it as SDD with a particular V tree, meaning SDDs are at least as succinct as OBDDs. And also, again, more recently, we also now have actually a unconditional exponential separation between SDDs and OBDDs. So again, here, I'll refer you to this paper for the details of the proof. But basically, he identified a sort of class of Boolean functions that'll have a cubic size SDD, but then, oops, I think there was some kind of a formatting error. So this is supposed to say 2 to the omega of n, of course. So basically, that function will have OBDDs of size that's exponential, right? And kind of, so the intuition is that the SDD that lets, or the V tree that lets you get an SDD of this polynomial size looks something like this in the case of for variables. So if you, basically the intuition is that if you want to take this V tree and then make it right linear to turn it into an OBDD, you get this exponential size blow up. So the fact that you can branch on multiple variables and not just one on the left side at all times is actually very, very useful when you think about the circuit size. Any questions? Okay, so because we're here to talk about database and AI, so here's a slide I kind of stole from Dan and Guy's tutorial some years ago. So basically, I'll try to kind of give you an intuition of what I understand about this, and Guy and Dan, please feel free to jump in. Right. So basically, this sort of Venn diagram is characterizing all the UCQ queries, unit conjunctive queries. So we have some non-hierarchical queries that are known to be sharply hard, and also some hierarchical ones. That's also I don't exactly know the intuition for this, how to characterize this. But basically, we have this dichotomy theorem from Dan's paper that shows that we have this separation within the hierarchical queries that's going to be polynomial time, and then everything outside being sharply hard. Right? And when you think about database query evaluation, one way to also evaluate them is actually compile them to circuits, right? Like run the compile to circuits and then evaluate the queries using circuit evaluation. So in that case, we care about the size of the circuits, size of the resulting compiled circuits, right? So basically, I think I also thought this was interesting that some like inversion-free or like the inversion-free for the inversion-free queries, OBDDs and SDDs are essentially equally succinct. And then we also have this result showing that some subset of these or polynomial time computable queries can actually be compiled into a polynomial size FBDD or decision DNF. At this point, I think this was a open question. I don't know if this is still true or.
That line is still open, and I
Okay.
don't think anybody worked on it. But I want to mention that Michael Monet over here made significant progress by showing that Q9 and QW, they can be captured by polynomial size DDNNFs plus, which they actually shortened to and call them DDs. It's a major result. So he's here. He can probably give us an impromptu talk one of these days.
Great, yeah, please do. Okay, anything more you want to add? Sure. All right. So I mentioned earlier about how is this characterization of trackability by the structural properties actually the right one, and specifically kind of how we've characterized the probabilistic queries, and some properties that we mentioned will actually give you tractable inference for those particular queries. So the question here really is, we've shown that, for example, to compute marginals, we want to have smoothness and decomposability on probabilistic circuits. So this is showing that these are sufficient conditions, right? So now the question is, are they actually necessary? Can you compute marginals without having either of those properties? So the answer in this case is actually yes. So note that I particularly said for inference by this feed-forward evaluation, they're necessary. Of course, if you have decomposability, you can always smooth the circuit, not in linear time, but still in polynomial time. So that means smoothness is technically not necessary for polytime compilation or polytime evaluation, but it's still, we actually show that it's necessary if you want to essentially compute marginal by this single feed-forward evaluation. And I think you can show this pretty easily by showing that without decomposability, you cannot decompose integrals downward, and you can actually make a pretty simple counterexample, right? So the other class of queries we saw was map, which we said that with determinism and decomposability, we can compute map also by just a single feed-forward evaluation, by just switching sums to max nodes. So in this case, we kind of said that you need the decomposability and determinism. We kind of lied slightly that decomposability is not necessary in this case. So it's a sufficient condition, but not actually a necessary condition. And there's actually a slightly weaker condition called consistency, or weak decomposability, which I think is honestly a better name, that actually suffices. right? So if we have determinism and consistency, we can also compute map tractably by just this single feed-forward evaluation. So what is actually consistency? So we say a circuit is consistent if for every product node, if any of its children share a variable, then that variable has to appear in just a single node, in a shared leaf node. Right? So this is an example of a consistent circuit. This is an inconsistent circuit because you have variable x2 appearing in both sides of this product node, but in two different leaf nodes. So if you think in terms of a logical circuit, this is basically saying if you have a shared variable, it needs to be either a positive literal in both cases or a negative literal in both cases. So of course, decomposability always implies consistency. If you don't have any shared variables between inputs to a product node, there's no additional additional check you need to do. So this makes it a weaker property than decomposability.
So for logical circuits, is it something more complicated than just saying that since it will appear with the same positive or negative value, you can just factor it out? Or is it this, or is it more complicated?
So if you have, let me try to remember. So I actually in a few slides down, I can actually show you in cases where you can turn a consistent circuit into a decomposable one by just essentially that's how it works by factoring it out. Right. So why is consistency actually sufficient for map? Just kind of going quickly here. For determinism, it's the same as before. So for consistency, to break down this max of products into a smaller or a smaller combination of queries, how we used decomposability was just saying that because this is a product of two like independent functions that they're depending on disjoint sets of variables, you can just optimize on each set of variables like independently. Okay? So here, they can have some shared variables, but you can still maximize them independently because any solution, any assignment you get as a result of the maximization. On the shared variables, they have to be the same assignment because they appear on through the same leaf node. So you can still kind of solve this optimization independently when you have only consistency but not decomposability. So why does this matter? The fact that decomposability is actually not necessary. It's because of this sort of, succinctness, of course, right? So if the question is if you only cared about map and not marginal, do you gain anything by enforcing consistency instead of the stronger properties, which is decomposability? So to kind of walk you through this sort of succinctness map involving these two classes or these two families of models. So we already essentially saw that turning a circuit deterministic is hard, meaning we have that smooth and decomposable circuits are strictly more succinct than deterministic ones. And there's actually a polynomial time algorithm to turn smooth and consistent circuit into smooth and decomposable ones. And this is basically where you can pull out a shared variable to the top if you have smoothness. The question is for the remaining remaining edges here. First, looking at this sort of example Boolean formula. So here, here we have these z variables marked with some I, j subscript. Basically, these ones all come from a set of variables in X, and they might have some shared variables. So this or this sum node is not smooth because these two variables may be different, maybe some different variables within X. It is deterministic because we have this product with Y and not Y variables. And also, it is consistent because in this giant product, all the shared all the shared variables all have to be like within X here, right? So all of these Z variables might be X, and they may be shared, but they always appear as positive literals. So there's this kind of variant of sharp, I believe, I think this was a counting, like a variant of counting like set two set was it? Yeah, problems that basically because this problem counting this problem is hard, we can show that we can't take this kind of circuit and then compute marginal on it, meaning we can't really turn it into a circuit that is decomposable. So that gives us this direction that turning deterministic and consistent circuits into a decomposable one is hard. And then we actually have the other results. So if you're starting with a circuit where you can compute marginals, right? So if the circuit is representing, for example, a naive Bayes distribution where we can compute marginals easily, on this kind of circuit, computing so on this naive Bayes distribution, if we marginalize out the class variable, that's still a smooth and decomposable circuit. But then if we try to perform map on this circuit that corresponds to solving marginal map on this starting naive Bayes distribution, which we know is actually NP hard, as was hinted earlier, meaning we get this result that between this families of models that can compute map and the one that we can that can compute marginals, neither is strictly more succinct than the other. Basically, kind of the takeaway is that if you care about one query but not the other, you want to be careful in choosing which properties you actually enforce. And of course, there's a lot of families of circuits that we can characterize by these properties. So we want to kind of complete the map, and I kind of presented this example at like a workshop, and then soon I think Stefan and Alexei published this paper that was kind of completing that picture, like this, with this nice hypercube showing relations between circuit families. So these are like arithmetic circuits with positive weights. And here, just as a legend, WD is referring to weak decomposability, which I've been referring to as consistency so far. Right? So hidden in here is kind of this 2D result saw, but they actually kind of completed the picture. And also, what was interesting is they also studied kind of the succinctness map between positive circuits, which is also unfortunately kind of a confusing name, but basically these are circuits that are guaranteed to have non-negative output, but are still allowed some negative weights, right? So in this case, that's more general. Like, what is the sort of what's the kind of implication on circuit sizes you have by imposing some structural properties, and there's actually still some kind of open questions there. And of course, there's also the question of succinctness between circuits with positive weights and circuits that are allowed to have negative weights, but still have to be positive in the output. I think in this paper, they also showed that in the case of, if you have determinism, they're basically equally succinct. But otherwise, I think there's some kind of subfamilies where they were able to show some separations, but also still kind of open edges in that domain. Okay. So hopefully, kind of answer some of your questions on how are the circuit size and tractability related, specifically in terms of the tractability characterized by the circuit properties. So next, what I want to talk about is some of the more sort of advanced reasoning algorithms we have, and how we can actually use them in some exciting applications. Okay, so here, so what we've seen so far in terms of tractable inference algorithms and coming up with those inference algorithms were, given some query, we're trying to identify some structural properties that would let you compute the query, for example, in feed-forward evaluation or some dynamic programming algorithm, right? And given a new query, you'd have to go and find again what's going to be the appropriate necessary and sufficient conditions for that particular new query. In this work from a couple of years ago, so what we wanted to ask was, given an arbitrary class of queries, is there a way to more systematically find what the sufficient and necessary properties are for that class of query, and come up with a inference algorithm reusing as much of sort of the existing algorithms and intuitions we have. So the approach here is going to be kind of characterizing queries as compositions of some simple operators. So these are the ones that we focused on. I think kind of do the intro of this, and then we can continue after the break. So the operators we looked at were the simple kind of sums and products of circuits, and also taking, for example, power or like logarithm of the function represented by the circuits. And these are just these operators already cover a lot of divergence and basically information theoretic questions you could ask. So the view is going to be taking a query of interest and then viewing it as a pipeline of these operators that take in circuits, do some operation, output another circuit, and have a whole pipeline that way. So to actually use a concrete example, let's say we're trying to compute a KL divergence between two distributions. Okay. So here, let's assume that both the distributions are given to us as probabilistic circuits. So looking at this definition of KL divergence, we can see that here the operators that's going to be involved are, for example, we start by taking a quotient or dividing probability given by P with the probability given by Q circuit. So that's one operator. Now, assume we can actually do this and represent the result of that as another circuit. So you can see that, okay, after that, what we want to do is take a logarithm of this output, intermediate circuit. And imagine we could also, we can again output this result of the logarithm as another circuit. Take the product of this with the initial circuit P. And if this result is a circuit that lets us compute marginals, basically arbitrary integrals, then we can just take this, compute the integral, and that gives us KL divergences of the starting two circuits. Right? And what's nice about this is we can, once we have these operators on the circuits, we can reuse them. So from before, we use the product and logarithm, just taking those two. We can also compute cross entropy between two circuits. So in cross entropy, what we have is take a log of one circuit, take the product of it with the original inputs, and then compute the integral over it. We can do this. We can so basically combine these operators in such a way to compute different queries. I think I can do a couple more slides. So to kind of characterize when we can perform this kind of operators on circuits, let me just introduce another property called compatibility. So this is kind of our first property that's going to be defined in terms of pairs of circuits, in terms of two circuits. So we'll say two probabilistic circuits are compatible if they have the same hierarchical scope partitioning, meaning you can essentially think of this as what we said earlier, which was structure decomposable, but with the same V tree. And compatibility kind of slightly generalizes that. For instance, to not require to conform to a binary V tree, but kind of intuitively you can think of them as two circuits that conform to the same V tree. Okay. This is an example of compatible pair of circuits. This one is not compatible because you can see that this product node doesn't have the same decomposition as these two also product node at the very top. So with this new property, if we have two circuits that are compatible and also smooth, then we can actually compute the product of those two, basically like multiplying two distributions, and then output the result as another circuit that's, again, smooth decomposable and also compatible with both of the input circuits. And the fact that we can kind of characterize what properties we'll have on the output is important because what we want to do next is actually compose these operators. Right? So we want to be able to say, okay, after I do this operations, we have properties X, Y, and Z so that I can apply another operator after that. Okay, so we'll stop here and then we can let's continue after the break. Yeah.
Okay. Any pressing questions? Mahmoud, I think you have.
How do we apply the log operator for a circuit? How do we produce a circuit that produces the log? Knowing that the log is not one of the gates that is allowed in a circuit.
Yeah, so that's actually the slide right after this. So I'll cover that more after the break. Well, again, it's based on some properties. So if you have some determinism in this case, then you can.
Log of the sum happens to be sum of the log because only one of the terms is non-zero. That's the idea.
Exactly, yeah.
That's gonna be.
So it's the same trick as turning max of sum into sum of max.
Okay, coffee time.